So we're going to get started here. Whoop. I'm going to take my coat off. We have about 90 minutes today, and depending on how many questions folks ask or how often people raise their hand in the middle of my demo to ask questions about what I'm doing or to look at things, we may or may not take up that full amount of time. And just to kind of set expectations for what's going to happen here, we have basically two correlated presentations that we are going to be sort of munging together into one longer session that's going to tell us a very interesting story about runtime security in Kubernetes and a tool that I'm working on that a lot of folks on the team and in the community have built called Falco, and how that's being used concretely in production in a way that we didn't expect it to be used, which I think makes for a good talk anytime there's a unique set of constraints or something happens that you weren't planning for. So I think the overall pattern of how we're going to do this today is I'm going to do a very low-level hacker-style presentation here in the command line, and I'm going to be sort of setting the stage, pun intended, for Falco and what we're going to be talking about today. And so when I'm up here, you're going to learn about the project, the CNCF. You're going to see it running in Kubernetes. We're going to do some scary things in Kubernetes, and we're going to play with the tools concretely to kind of understand this open source tool and where it came from and where it's going. And then Abhinav here, my co-presenter, is going to come up, and he's going to talk about how he uses this running in production in a way that it's similar to what I'm going to be talking about. But I think when you hear from one of the maintainers of the project why we did what we did, and then seeing how Abhinav and folks at Frame.io are using it, I think it's a pretty good thought experiment just to remind ourselves that when you are building open source technology, there's things that you may not be prepared for that could happen. And that's a general sentiment that we're going to be going through today, this concept of things that you weren't prepared for, and for how do you prepare yourself for them, right? How do you get ready for something that you don't understand or you don't anticipate is going to happen? So anyway, we're going to run my slides in the terminal. My talk here, all of my slides, everything I do is going to be in the command line. So if we want, I don't know if we can maybe dim the lights, or if folks can see this. Does anybody want me to switch to a higher contrast? That looks good. A higher contrast view here. You don't have to raise your hand. You can just shout it out. If you want to move to the front, if you want to see more, this is about what it's going to look like on the screen for folks at home. I see lots of thumbs ups. I see more thumbs up, lots of thumbs ups. Yeah, okay, everybody just put thumbs up. Last chance to shout out for higher contrast. Going once. Okay. Again, if at any point you're missing something or you can't read something, raise your hand. I can zoom in, or we can switch. So I'm giving this talk to you because I want you all to walk away feeling successful at the end of this. And speaking of you, I'm about to talk about me for a few minutes, but let's find out more about all of you lovely people in the audience, and we're going to kind of cater my presentation to folks here in the audience. So I do this at the beginning of most of my talks, and I've been doing this at KubeCon for a few years, and it's really interesting to see how the ratios have changed over the years. So hands in the air, running Kubernetes in production. Bam! The entire room just put their hand up. Hands in the air, who here has ran a Docker container? Who here has has written code to launch a container in C? Leo, my main man, has his hand. Oh, we have another one back over here. Okay, we might do that today if we get there. We'll see how this goes. Okay, and who here knows what Falco is? Who here has run Falco? Okay, who here is running Falco in production? Okay, you should see me afterwards. We would love to talk more and get you some free Falco swag, and see if we can't get you in our official adopters.md file. And speaking of Falco swag, if you answer questions that I have limited edition magnetic Falco pins up here, and we can get you a Falco t-shirt as well sent out to you after the conference. So if I ask questions, there is some incentive to answer. Okay, so without further ado, we are going to view these illustrious slides of mine that are in very high quality 64 columns of pure Unicode. Yay, our first slide. Okay. So yeah, this is actually cool. I had to invent my own markdown language for this. And you can sort of see how all of this works. Oh, and really quick, let me just change something. We're gonna start over. Go source github.com, Falco Security, Falco slides. I want to make sure that folks have a link on the screen. And so what we're going to do is we are going to do this and GitHub, Kris Nova, public speaking, slides, bam. And now you should be able to get your cell phones out and take a picture of the bottom left corner of the screen. Okay, I just missed this bit.ly link here. If you want to grab a photo of that, everything that I'm going to be talking about and Abhinav's going to be talking about, you're going to be able to reach from that bit.ly link. And it's going to be on every slide, so feel free to take a picture of it whenever you want. And then that's going to help us justify that what we're talking about today is important and people care. So we're going to talk about cloud native runtime security with Falco. I am your host for the first half of this. My name is Kris Nova. I work at a company called Sysdig. A little bit about me. I am an O'Reilly Media author. I wrote the book on cloud native infrastructure, literally. If you have an opportunity to buy several copies of it for your friends and family, please do, and then buy some more copies. And I am a maintainer. I actually just got done doing a CNCF interview today about all the projects I've been maintaining or have maintained or currently maintain or I've worked on. I've been around cloud native probably since 2015-ish. I've worked on KubeCon Kops, KubeAdmin, SIG Cluster Lifecycle, SIG AWS. I've contributed to Go, Terraform. There's a lot of things that I've worked on. And I just like to help out the community, and I'm constantly hacking and tinkering on things. And over the years, I guess people have enjoyed the things I have to say, and here I am. So now let's talk about this thing called runtime security. Who here thinks they have a good idea of what runtime security means? We have a couple of hands go. OK, pretty good set of hands go up. So I'm going to talk about what I think runtime security is. And I'm going to talk about why I think that's important. And my opinions here aren't necessarily the right way. They're just my opinions. And I encourage everybody here to question this and to start thinking about security in general. Because if you look at my career, honestly, in the past 5 years in cloud native, there's been this pattern of bits and pieces of the cloud native ecosystem, particularly around Kubernetes, that were incomplete. The first one that I was very excited about solving was the infrastructure problem. When Kubernetes first came out, we said, no, we're not going to tell you how to install Kubernetes. That's outside of scope of the project. And that was frustrating for folks who, well, frankly, wanted to install Kubernetes. And so that was one of the first tools I worked on. And if you look, there's been this pattern of the space growing. And different subsections or different components of cloud native around Kubernetes growing based on these gaps in what we have easily accessible tooling around. And I think we're kind of at this point where Kubernetes is starting to level off. And there's maybe one or two really big holes in the global pie chart here. And in my mind, one of the biggest ones is security. How do you secure a Kubernetes cluster? And what does security even mean? Like, where does it start? Where does it stop? And like, I've been on Twitter. I've written a few blogs about this. And I think just starting to question what security means and what runtime security means, I think is important. And so the three kind of buzzwords I have that come to mind when I think of runtime security is it's a fancy word, anomaly detection, which basically means, in my mind, something bad or confusing happened that we weren't prepared for, and we just kind of want to know about it, or at least be able to go back and get some information about this thing that we weren't expecting to happen. Forensics, so this is like the detective work. This is like, like we've all seen Detective Pikachu, right, with his hat and his magnifying glass, going in and actually trying to solve the mystery of the privilege escalated container of 2019. And then last but not least, stability, right? Runtime security, in my mind, is our last line of defense. We're going to talk a little bit more about that in a moment. And it's critical for this layer of software to be stable, right? We don't want to have the one piece of software that we're counting on in an emergency to save us to break our computer or to crash or to not work or to fail. So I think it's absolutely critical that this is stable, and we're going to look at some interesting patterns in Kubernetes and in the Linux kernel that sort of ensure that we're writing some pretty stable code here. Okay, so I have been talking to a lot of folks here at KubeCon over the past few days and on the internet over the past few weeks. And one of the big pieces of feedback that I've got is we're kind of in a very similar situation to what Docker was in a few years ago, which is we have some language and some naming confusion. We all know naming is the hardest part of writing software. So I'm going to spend a few moments here and just clarifying 3 very important actors in the field here. The first one, Sysdig, the company who pays me. I work there, and we are a bunch of low-level hackers. We hang out all around the world. We have an office in San Francisco, and a bunch of really smart folks I get to work with, and we write a lot of C and C++ and get to do fun stuff with the kernel. So Sysdig, the company, is effectively an evolution of Wireshark. Wireshark, show of hands, who here has ran it? Yeah, everybody just put their hands up. So our founder, Loris, a great friend of mine, he was one of the original authors of Wireshark. And if you look, there's some similarities into what Sysdig does. And I think the big thing to start to imagine here is Wireshark said, if we want to find the ultimate source of truth, right? Like in my mind, this is like the quantum particle of computer observability. Like what's the most fundamental element that can always tell us what's exactly going on? And the original thesis was the network. If it's a TCP packet, that's the ultimate source of truth. You can't get any smaller than that. And like good scientists, we continue to push our field forward. So now that we're in cloud native, we have virtual networks effectively, and we could have 2 containerized processes running on the same node, talking to each other on the loopback interface, who believe that they're talking across some network, but really it's just a synthetic network that the kernel is allowing us to create. And so we have taken it a step further, and we said the network is good, but the kernel is better. So that's sort of the philosophy behind the company. And so we see that reflected in one of our open source tools that we call Sysdig. Same name, very confusing, right? Anyway, this is a CLI tool. Show of hands, who here has ran this before? It's similar to strace, except for it sort of works globally, and it has a little bit more enriched meta information about what's going on in the kernel. But basically, when you look at how a process interfaces with the kernel, it ultimately translates everything it's doing through the syscall interface, usually using a library like glibc. And those go into the kernel, and what we do is we just simply track those. We trace, it's called kernel tracing. Every event in the kernel is a function executed, and we trace those events. And we send those back up above the kernel into what we call user space, and then with those metrics, we have this crazy idea that we will be able to tell some sort of story with these metrics, which is where Falco comes into play. Here in a moment, I'm going to do a demo, and I'll show you the Sysdig tool and the fire hose of data that comes out of it. And then we're going to run Falco, and you'll be able to see it's actually much neater and cleaner and much more human-readable and human-friendly to actually put together a story or to start to do that detective work of what's going on a system. So Falco is a CNCF project. It basically uses these 2 libraries that are open source called libscap and libsensp. And we are able to take kernel metrics and enrich it and go a step further with the Docker context. If you're using Docker or cryo context, we're basically able to pull meta information out of the system and enrich our kernel tracing events with that. And then we're also able to do that with the Kubernetes meta information and audit logs as well. So we're able to put together this really nice enriched object that spans multiple layers of the stack, starting at the lowest, most fundamental layer and going all the way up to Kubernetes. And we're able to tell a story using all of these inputs. And we're going to explore Falco a little bit today. So again, it's a CNCF project. If you go to cncf.io, you can find more about Falco, and there'll be some links here. And that link in the bottom will get you there as well. OK. So the history of Falco. It was originally created as an engine to parse libscap and libsensp. And when we say engine, basically what we mean is it is those 2 libraries wrapped up in a for loop and runs as a daemon with a signal handler. Very, very fancy, I know. So this was donated to the CNCF. It was originally created at Sysdig, and I had joined the company about 3 months ago, and I've been working on making this as hygienic and healthy of an open source project as possible. So if you're interested in security, we would love to invite you to come join the party and hang out with us and start hacking on the kernel. Right now, the majority of Falco is written in C++. Raise your hand if you write C++ and you like it. Okay, 2 hands, okay. Raise your hand if you like Go, Python, other, yeah, everybody just put their hands up. Okay, and we'll talk more about this later, but we're working on building some handy API interfaces for Falco that's written in C++ for a number of reasons, particularly when it comes to auditing the kernel. And then how we're able to take that and we're able to have effectively a client Go or a client Python or a client Ruby so that you can start building tooling on top of Falco so that you don't have to worry about the nitty-gritty C++ implementation bits. Here's my very fancy diagram in ASCII art. So let's start at the bottom. I feel like a lot of folks, especially in security, like to start at the top and go down. We're going to flip that around and we're going to go from the bottom up. Okay, so the bottom half, you can see there's that line in the middle. The bottom half of this represents the Linux kernel. And here you can see we have 2 main avenues of running code in the kernel, one of which is the more conventional approach, the kernel module. The other one is a newer approach, the EBPF approach. Who here has written a kernel module? Who here has written an EBPF probe? Okay, I think Leo's put his hand up for every one of these. And basically what these do is these solve the problem of, hi, I'm a software engineer, and I would like to run logic in the kernel. In the same way that there's somebody who said on Twitter the other day, I forget who it was, I'll add it to the comments after this, but they said basically EBPF is to the kernel as JavaScript is to HTML. And what that means to me is you're able to create custom logic and then run that in the kernel, right? And that's how we're able to pull these metrics up and start to understand what's going on from the kernel level. So the problem with a kernel module is that if you write a bad or a buggy kernel module, you can break your system. Because the kernel is going to, basically, you're going to hook into the kernel's process, and then you're going to take some action. And if something goes wrong while you're taking action, the kernel is going to wait, and it's going to halt on that. And you could put your computer into deadlock pretty easily just by a very simple bug. So that's where eBPF comes into play. And eBPF is brilliant because what it does is it actually has code that's already pre-written for you in the kernel. And it's been tested. It's gone through the same Linux testing suite that we use for all of our releases. And we basically just tell the kernel to turn on or off various pieces of eBPF that are running in a virtual machine in the kernel. So we're not actually writing custom code. We're just saying, hey, kernel, you weren't executing this code before, but would you mind please also executing this little bit of code along the way? And then we can pull that up into user land, and we can start to make sense of it. One of the features that eBPF supports, you guessed it, kernel tracing. So anytime you execute a syscall, you're then able to begin to understand those syscalls up in user land. So those are the 2 approaches. The caveat here is eBPF requires a newer kernel, 4.14-ish, to execute a lot of the stuff that we use in Falco, whereas if you're running in an older kernel, the kernel module is going to be the way to do that. So obviously there's some pros and cons with each of those. So then that goes into a ring buffer where we have 16 megabytes. I know, it's a lot. 16 megabytes of memory per core of information that comes up from the kernel. And this is just stuff that's going on in your system. And then we have these 2 libraries in user space that just pop events off of that ring buffer. And the beauty of the ring buffer approach here is as it circles around, imagine a clock, right? The hand going around a clock. As it circles around, it's leaving the previous events before it, and it won't overwrite events until it circles 360 degrees back around, which means at any given instance, if this has been running for a period of time, we have 16 megabytes of history that we can go back and observe if needed. So this is where we're starting to tell these stories and starting to gather information and doing what we call runtime security. So we're able to respond to events at runtime effectively by looking back in time in this buffer that we have in memory. And all of that goes to Falco, and then all that can ultimately go to gRPC endpoint that you lovely software engineers can use to plug up and plug into anything you want effectively. And we're going to do a demo later, so you'll be able to kind of see concretely how all of this works. So let's talk about Falco. So now that we understand how we're getting the syscall information into Falco, we want to talk about other input streams that we have. So obviously the syscalls that we're pulling out of the kernel tracing, either through a kernel module or an eBPF probe, are going to be important, and that's probably the most exciting bit of what Falco can do. But we're also, like I mentioned earlier, we're able to get the container context. This is going to be the container ID, the image that the container is running on, all of this wonderful meta information about what's going on. And the last input stream we have, there's actually two here that I kind of munged into one, which is Kubernetes meta information. What's the name of the pod? What namespace is it running in? What are the labels? As well as the audit log information. Who did what and when did they do it? And again, this is where we're starting to look at telling a story of being a detective, of understanding our systems at a fundamental full stack level, instead of just at the kernel or instead of just in user land. We're going and spanning the entire system with Falco. We simply assert these input streams against a set of rules. And we're going to look at some of these rules in a moment. And then if one of those rules is violated, we plummet through to an output. And here we have 3 outputs that I put up on the screen, and we have more coming, and there's actually a lot more that Falco can do, but I picked the 3 that I think are going to resonate with you the most. The first one I've mentioned a few times already. We have a TLS, mutually encrypted gRPC endpoint, and we have clients that generate code using protobuf that you can consume this endpoint with. We have a webhook. In the exact same way the Kubernetes audit log would reach out and send a request to a configured webhook, Falco can do the same thing. Falco can curl an API. Falco can go through and effectively take any action over HTTP or HTTPS that you want. Last but not least, and this is great because a lot of the C and C++ engineers I get to work with consider this a higher level feature of Falco, it can go to standard out, which is what we're going to look at here in a moment. But just as you're looking at standard out, I want you to imagine that this could be effectively plumbed through to anything else as well. And we have some demos on that if you want to see those, come find me afterwards. Okay. So let's talk about the problem of runtime security. Now that you kind of understand Falco and how it works, let's talk about how we got here, right? Like how did we go from this idea that I'm about to explain to that code and that system that we just looked at? So I'm going to ask a few questions here. And these were the questions that we began to ask ourselves as we started to explore how we were going to solve this problem. What happens when access control fails? And what we mean by that is a lot of security is implemented by preventative action. Locking the door, setting an alarm, saying, hey, if we can prevent folks from doing things that we consider malicious, we're going to secure our system. And that is a fundamental part of securing a system and probably the most effective way to get started with securing your system. And the concern here is every time somebody has a catastrophe, a car is broken into, a bank is broken into, your house is broken into, something happens that you aren't anticipating, somebody does something to attack you, they usually don't care if you have door locks set, right? They've found some way to bypass the door locks, and this is where the second layer that maybe is only applicable a very small portion of the time, but it's going to be applicable during the most important time, which is when something happens you weren't prepared for. So in my mind, we need both of these in place to truly secure a system. So what do we do when catastrophe strikes? And then last but not least, after catastrophe strikes, how do we tell the story? How do we begin to look at all of the data and actually make sense of it and actually come and be able to put together this person from this IP address came to this container and did this and installed a Bitcoin miner, and here we are. And I can give you all the information to demonstrate that this is beyond the shadow of a doubt, in fact, what happened. And that's what we try to solve with Falco. So here are the 3 common approaches to solving both prevention as well as forensics analysis or surveillance after a catastrophe has happened. So the first one is using a concept called LD Preload, which I'm going to high level this. There's a lot of great resources on the internet, and I don't want to bore folks with reading the LD Preload man pages, which I have done in the past, and you can go to YouTube and watch me read those on stage. It's quite fun. But basically, in order for you to use LD Preload, what you would do is you would write some code, usually in C, and you would effectively hook into the G standard library glibc. And when an executable program that was written by either yourself or another engineer tries to access the C standard library, if you use LD preload and you wrote the LD preload library you're loading correctly, you would effectively be able to intercept that function call, take some action, and in most cases, you would then take a small amount of action, hopefully nothing too invasive or blocking, and then you would hand that off to the original function that the user was trying to call. Now this is great because this solves the problem of like, all we have to do is wrap every glibc publicly exposed function or method to a log file, and we can start to see what's happening behind the scenes. There's a problem here. Who here has written Go? Okay, so Go doesn't use glibc, so right away that's not going to work here. So that was one of the things that we started to explore. And we said, okay, so LD preload is good, but it can be better. So the next thing we went and we said, okay, let's talk about sidecars. Who here has ran a sidecar before? Great. So sidecars run in the same context in the system space as the original processee. So if you go and you read in the Kubernetes documentation, it says like a pod has shared networking and shared storage, which means if I have two container processes running in a pod, they can communicate to each other via localhost 127.0.0.1. Which is great, but if you look at how containers are actually created and what a container looks like at runtime, that sidecar is effectively in the same system space as the original container. In other words, it's in the same set of namespaces and probably C groups as the original container, meaning that if somebody was to escalate out of that container or do something outside of that context, the sidecar would effectively be blind to it. And we would be able to use the Linux kernel and all of its wonderful namespacey goodness against the container sidecar that we would be hoping on to secure our process. So we said sidecars aren't going to do it. So then we looked at kernel modules. This allows us to write arbitrary code in the kernel, but like I mentioned earlier, these could potentially crash a kernel. So it's a little bit better than LD preload, but there's still some risk here. Furthermore, like if we're already not scared enough apt-get installing random package.dpkg from the internet, we're now effectively telling people to, yeah, just trust us and run our kernel module in your kernel. We're a security company. We're not going to do anything too scary here. So there was some concern there, particularly about loading custom logic into your Linux kernel, probably the most intimate part of your system. Okay, so let's kind of summarize this here. So we looked at those three approaches. We've understood that kernel modules are the best of those three, but eBPF is really where we want to move going forward. And so to summarize the problem again, kind of looking at it differently now that we know the possible avenues of solving the problem, the first thing we want to solve is prevention. In the same way that SE Linux prevents you from executing various bits and pieces of the kernel, we would potentially want to prevent folks in our system, such as a Kubernetes cluster, from taking action. This is where tools like RBAC or tools like OPA come into play, because you can effectively say, no, you have your labels configured incorrectly, or no, there's some string that doesn't match this pattern that we've defined, and we're going to prevent you from taking action. We're going to tell you no. And if you look at the way that admission controllers in Kubernetes work, they basically allow you to hook into a process and reject a request to take change or mutate an object in the API server. And so that's prevention, which again, this is the first step most folks take, and probably the first step I would encourage folks to take. But prevention doesn't always complete the story. So we want to start taking security seriously in the enterprise and looking at how do we respond to events that we aren't prepared for, which is where runtime security and forensics comes into play. So again, these are useful in the very small edge cases, but if you have this installed, this is going to be the difference between a total catastrophe and at least a catastrophe that you can understand and prevent moving forward and draft some policy around. And again, this is sort of our last line of defense here. So when all else fails, where do we turn to? What do we look to to try to solve our problems and make sure that this does not happen again? So I'm going to give a quick history of eBPF, and I hope folks here get excited about this. And we're going to talk a little bit more about how you can find out more about eBPF moving forward, but I'm just going to give you a quick high-level overview for my demo so that you kind of understand what I'm showing on the screen here. So who here has heard of the Berkeley packet filter? Okay, and who here knows the difference between that and eBPF? Cool, handful of folks. So basically, I think the analogy I like to use is BBPF, BPF is to EBPF as them is to, or as VI is to them, right? It's extended Berkeley packet filter, right? So it's just an improved version of the original BPF work that was done. And as I always say, like BPF, we're going to party like it's 1992. This has been around for quite some time. So we're going to explore kind of what it is and how it works. OK, so let's remind ourselves of our use case. We want to trace all kernel events into and out of the kernel. So every syscall has two fundamental parts, right? The syscall coming into the kernel and the return value coming out of the kernel. So there's two events there that we want to trace. We eventually want to enrich that data about what was happening with metadata. We want this to be stable. We don't want to run the risk of breaking our system or running a potentially malicious or invasive kernel module. And we want to be able to audit this in user space. So we had a pretty tall order here if you think about what we're actually asking the kernel to do. And eBPF in this case was a perfect solution for us. So again, let's look at the problems with the kernel module approach. Number one, it was invasive. Folks were hesitant to load new kernel modules into production for good reason. And it was risky. Buggy kernel modules can crash kernels and block kernel processing. And no matter how well tested your code is, as I've been saying this entire time, things happen that you're not prepared for. And there are always going to be edge cases, and there's no such thing as perfect technology. So again, eBPF gets us closer to that zero level that we're so desperately trying to reach. So how eBPF works. Like I mentioned earlier, the code is already written, and we're just turning it on. There's a virtual machine that is compiled into the kernel. In fact, you can go to github.com/torvalds/Linux, I think /BPF, I think it's in the top level directory, and you can actually see the code that folks have been working on, and you can see it's been very recently committed to. So it runs as a virtual machine. It builds these dynamic maps in memory, and we can access those from user space. Furthermore, this is another interesting feature that is an improvement on kernel modules. We can dynamically load via a BPF system call our BPF program that we want to start using. And we can use eBPF for networking analysis, for kernel tracing. There's a whole arsenal of things that it can do for us. And again, the code is pre-written, and we're just taking advantage of it. If you're interested in finding out more, because again, I'm keeping this kind of high level for this talk because we have a lot to go through. There's two links here if you want to snap a photo, and these are in that bit.ly link as well. The first one is a blog written by an engineer at Sysdig named Gianluca. He's the one who wrote the eBPF probe that we use to this day. And the next one is a link to the BPPF observability in Linux book that one of our engineers, Lorenzo Fontana, wrote that we've been giving away at the Sysdig booth. So if you want to grab a free PDF of that, go to the bottom link and you can get it for free. And if you want an actual hard copy of the book, come find me or Leonardo or Lorenzo or join the Falco Slack, and we're happy to figure out a way to facilitate you getting a hard copy of the book. And that goes into great detail with runnable examples that are hosted in GitHub that you can go and start to tinker with BPF with. OK. So I need somebody to shout out a word, because we're going to run an experiment. The sillier the word, the better. Anybody say a funny word? Banana. OK, so we are going to run the banana experiment. So what we're going to do is we're going to demonstrate using the open syscall. This is a very simple syscall. Basically, this just opens up a file for reading or writing using the kernel. 10 minutes? OK. The next thing we do is we're gonna replicate the banana experiment. It's a good word, I like it already, in 3 different environments. One in raw Linux, one in a container, and one in Kubernetes. And we're gonna perform the exact same experiment in all 3 environments, and we're gonna see what the kernel does using Falco. Falco is gonna give us visibility into the kernel, and we're gonna understand what kind of information we're able to get and actually see me do something scary, and we're gonna see what Falco has to say about it. And so the goals here, we want to understand the importance of surveillance, of tracking these logs over time, and we want to understand complete system auditing, right? So like, this should show you that auditing the system from the kernel up is going to give you the information that you can get regardless of how the banana experiment is ran. Regardless of if it's ran in a regular old Linux process, in a container, or in a pod in Amazon, the banana experiment has some pretty interesting outcomes based on running the same thing over and over again. OK, so how we're going to do this is I have Falco running a daemon set in Kubernetes. That's going to be our final example here. And we're going to do open in native Linux, open in Docker, and open in Kubernetes where Falco is running as a daemon set. And hopefully this will show you how Falco works, and you'll understand why we did what we did. And then we're going to get Abhinav here to come up on stage and tell you about how he's using this in a completely different way than we expected and how it's still useful for them and their team. So let's look at Falco. So the first thing I want to do is I'm going to run sudo falco. Should I zoom in? Can folks see this OK? Yep, cool. OK, so you can see here, not very much is happening. Because Falco is taking this fire hose of syscall information. Oh, this is Chrome yelling at me right now. This fire hose of syscall information, and it's asserting if it's violating a rule. And as Chrome just did a set UID, it violated a rule, and Falco yelled at us. And so if you want to see what the actual syscall information looks like coming out of the kernel without those set of rules filtering it, we can run the Sysdig CLI tool. And I'll enter my password. And as you can see, there's a small amount of data coming out of the kernel right now. And most of this is my GNOME terminal, but I probably have Zoom or Slack doing some crazy stuff behind the scenes. But you can begin to see here, we have reading, we have writing, we have syscall information, we have the arguments that are passed to these syscalls, and you can see the process ID, whether it's an event in the kernel that's going in or an event in the kernel that's going out. So this is great, but this doesn't really tell much of a story unless you know exactly what you're looking for. So what Falco does is it allows you to write some rules that say if we detect patterns in this set of data, we want to start knowing about it. We want to start alerting about it. And so in this example, when I ran Falco in the other terminal here, you can see we have this notice, right? So this is Chrome doing a set UID, and Falco said, OK, this isn't super invasive, but you probably might want to know about this in the future. But we're going to do something a little more invasive here on my laptop. So in a third terminal, I'm going to do this, and I'll zoom in. I am going to touch user local bin banana. B-A-N-A-N-A. What is this? B-A-N-A-N. Did I spell that right? Banana. OK, yeah. Sorry, I'm like singing Gwen Stefani up here. So anyway, we're going to touch this. And in order to create an empty file, we, of course, have to call open. So we need to escalate to root in order to do this, because my user local bin is, of course, protected. So sudo bang bang, enter my password here. And now let's go see what Falco has to say. We scroll down, and we have some really interesting bits of output here. The first one, it says, notice shell history has been deleted or renamed. What's happening there is I'm running different terminals as the same user. So whenever I create a new terminal session, which I just did, bash history resets. And Falco doesn't like that when that happens, because that's potentially somebody covering up their tracks. So again, using syscall information, we can start telling a story. And if you look at the end of this here, you can see that we have some NA fields. And this is going to be relevant in a moment when we run in a container, particularly the container image that we're going to see down here. Notice we have no container image defined because we're not running a container right now. But if you look at this error, we got an error this time. It says file below a monitored directory open for writing. And then you can see we're actually able to get meaningful information out of the kernel. The user, for instance, the command that I ran, it's user local bin banana. And you can see that we're actually able to start painting a picture here and taking action. And remind yourself that this is going to standard out in this example, but you could plumb this up to whatever software you wanted. So let's replicate the banana experiment again. So in this case, we're going to do a Docker run IT. Somebody shout out the name of a container image. Bash? I'll do Alpine, because mountains, come on. Docker run IT. Thank you. Is it bench shell or just shell? Thank you. OK, there we go. We'll clear our screen. Banana experiment again. And here, the first error, notice the shell was spawned in a container with an attached terminal. Yeah, we would probably want to know about that. And we're getting meta information from the Docker context, the Docker socket, and we're starting to plumb that into Falco as well. So Falco's smart enough to start auditing and understanding what's going on. And you can see here from the kernel's perspective, it's the exact same behavior. Because it's an isolated process running in a unique namespace, the kernel processes it exactly like if it was on the host system. So by auditing at the kernel level, this is like the big lesson here, you are actually able to, the kernel is truly synthesized into believing what you're doing in a container is actually happening on a real, true, authentic Linux system. So this is great because regardless if you're running in Kubernetes or on a Linux system, having Falco, you will be able to audit across the stack, right? So you could take a Java process and you would be able to start getting similar metrics to this one as you would if it was running in a container or Python or anything else. So the next thing we're going to do here is I have alias kubectl is equal to k. So if I do k get pods, you can see here that I'm going to list pods in my AWS cluster. And you can see if I do k get nodes, you can see I have a Kubernetes version 1.13 running in EC2, 2 nodes and 1 master. So let's list pods in the Falco namespace. You can see here Falco is running as a daemon set, and we have 2 Falco containers, or pods rather, running on each of those nodes. So what we're going to do here is we're going to tail the Falco logs, and you're going to notice that we're actually getting a lot of information out of Kubernetes right out the bat. So how we're going to do that is we're going to do k logs namespace Falco, label app is equal to Falco minus f. And you can see here we've got a lot of things in here. Let me clean this up a bit. Okay, 3 minutes, and then I'm going to wrap up. Okay, so you can see here we're getting really valuable information about what's going on in my cluster. And I've already kind of demoed this before I walked on stage, so you can see we've already got some alerts, but we're going to generate some new ones here. But we're going to get the Kubernetes meta information as well as the audit logs as well. So how we're going to do that, I'm just going to finish this demo, and then I'll be ready to go. How we're going to do that is we're going to do krun nginx -- image nginx. We'll do bin bash. We did Alpine before. We'll do nginx now. And we do kget pods, and we can actually exec into this pod here. Kexec it, here again, bin bash. What's going on here? Kget pods. Okay, let's do this. Krun alpine, image alpine. Kget po. Let's try this one. Kexec it, the name of our pod, sh. Container not found, alpine. Okay, well, I'm not going to debug Kubernetes live on, on the screen here. So we're going to just look at some of the, I did this earlier, I have no idea. I'm going to blame it on conference Wi-Fi, even though that doesn't make any sense. But we can see here I did the banana experiment earlier. Notice a shell was spawned in a container. In this case, I ran a different command. Let's see if I can find it here. Well, the point I'm trying to make here is if you look at one of these output logs, you can see we're actually able to get the container ID, the namespace that it's running in. And you can see here I ran a container earlier called Scary, and it's running the container ID, the name of the pod is Scary, the namespace is default. And we're starting to get information from the Kubernetes audit logs about who's doing this. And the takeaway here is you're starting to tell a story with Falco auditing at the kernel level with all of the information we're getting from Kubernetes as well. So anyway, that's my little pitch here on runtime security and how we want to start auditing at runtime to understand problems that are happening with Kubernetes or a Linux system behind the scenes. And we've open sourced this because we think it's a good idea, and we want folks to get involved. And we were very, very surprised when our friends over at frame.io reached out to us and began telling us how they had taken this technology and implementing it on their end. So I'm going to let Abhinav get up here and show you all a little bit about what they were being able to do with the same basic piece of technology now that you understand how it works. Yeah, you can clap. Why not? And why he gets his sessions put up, does anybody have any questions for me? Here you go. Yeah, what's up?
So I know the answer is probably probably it depends, but any examples of how much time you can fit into that 16 meg frame buffer?
So it depends. It really does. So it's obviously directly correlated to the amount of noise that your kernel is generating. But usually a 16 megabyte capture, I would say like you could probably look a good 60 seconds back in time. On a relatively like average sized computer with a relatively average sized workload. But again, that's like the down the middle answer. Depending on what you're doing, expect that to go greater or less. Any other questions? Yep, one right here. Have we thought about structured output from Falco? So yeah, so if you looked at the standard out that was on the screen, what we have is for every one of our rules that are defined in YAML, you actually define an output string, and we have variables that you put in there, and it works like a templating language. And in that case, it was just the tip of the iceberg. We only pulled maybe 6 or 7 metrics into that output string when we obviously have a lot more in memory. So if you were to use the client, you would get the full object with all of the information baked into it, and you could do whatever you want to with it then. Cool?
Cool. Oh, can you hear me? Okay. Awesome. Good afternoon, guys. My name is Abhinav Srivastava, and I'm a VP and Head of Information Security at Frame.io, a New York City startup. Before joining Frame, I spent 6 years in AT&T research, working on cloud security, SDN, and other projects. And before that, I spent 5 great years in Georgia Tech working on my PhD in computer science, where I worked on virtualization security, operating system, and system security. And today I'll be talking about how we enhance Falco by building custom toolings around it and customize it to our environment and to our needs. You have seen Kris's hacking slide, and let me take you to the world of marketing slides. So what is Frame.io? Let me give you a quick 2 minutes overview. So Frame.io is a video review and collaboration platform. We allow users to upload their media contents or work in progress contents into our platform, then invite team members and clients to collaborate on the project. So we are essentially building the video cloud. We are not a creation tool, we are a collaboration tool. So think of us as a GitHub for videos. And we are entirely hosted in Amazon AWS. So the first thing that we allow teams to communicate clearly. They can communicate or collaborate on the video itself, right? Not just about the video, not using long email threads. So users can annotate the video and insert comments on the video itself that gets embedded with the frame. And you can easily click on those comments, and you can do easy navigation to find out who is doing what. Second thing that we allow, we act as a secure hub for film productions. So teams can control that who can see what and what they can do with those videos. And it also allows them to easily organize the different versions of the single video. Finally, we allow teams to share content because sometimes when you work with certain collaborators, they are outside the platform, right? Sometimes executives want to see the cut of the video before it gets released. And you can use secure sharing feature to share content with external partners. And you can also decide or customize what and how they see those content. So as I said that we are not a video creation tool, we are a collaboration tool, but we have integrated ourselves to a variety of video creation tools. For example, Adobe Premiere, Effects, Media Composer, DaVinci Resolve, and we have a native integration with the Final Cut Pro X as well. And this value proposition has enabled us to accumulate a great set of logos over the past few years. And a bunch of logos you can all recognize, and these all are our enterprise customers. So this is a high-level overview of the platform, and let's see how actually it gets translated into the actual platform that enabled all these features. So we are a containerized platform. We use EKS cluster, ECS cluster. And you can see that, as I said, we are entirely hosted in Amazon AWS. So when the user sends a request, it goes to AWS Web Application Firewall, then goes to load balancer, and depending on the request type, it either hits the EKS cluster or ECS cluster. Behind the scene, we use Postgres or a database for storing the transactions, and all uploaded videos are stored inside the S3 bucket. And we process two kinds of workloads. Very important to understand for the future slides as well. That first kind of workload is related to web requests, right? When the user sends a web request for creating a project, creating a team member, and those kind of simple API exercise. That's one kind of request that we process in our platform. But second, and a specialized request that we process is related to video transcoding. So anytime when a customer uploads a high resolution content, what we do, we take that video and we transcode that video and generate a lot of low resolution proxies, so that even the devices or clients that are resource constrained or bandwidth constrained, still they can collaborate on the video. And that entirely is a separate pipeline running ECS cluster. So with that knowledge, with that background, let's see some of the metrics related to containers. So every day, we boot almost 300,000 containers, right? So we don't know whether it's too many containers or too less containers. We haven't checked with other industries. But yeah, in our platform, on a peak day, we are running 300,000 containers, which roughly translates to 13,000 containers per hour. And as I said, that these containers are either processing web requests or doing transcoding jobs. So that's when they span from seconds to hours, right? Depending on the length of videos that is being uploaded. If, let's say, user is uploading very short video, then transcoding can finish very quickly, and that containers may last just for a few seconds. But if the video that is being uploaded is very long, it might take hours to transcode that video, and that's when those containers runs for hours. And any container that is processing user web requests is also long-running containers. And a fun fact that every hour we do 10 days amount of work because we run that many containers, and we are running all of them concurrently. So we are containerized platform, we run that many containers, so how do we protect those containers? So for that, we have two requirements, right? We want to have a complete visibility inside our containers, and then we also want them to be secure, right? So that if there is an attack going on, we would like to know. So what do we mean by visibility? Visibility means that we would like to know what processes are running, what files are being opened inside the container, or what connections are being created, right? Because that's when we will now find out if somebody has uploaded something, and that basically compromised the container, or some user request has bypassed our firewall and all those things, and our containers are compromised. So we would like to have a visibility inside the container to know what is happening. While security and visibility go hand in hand, the same questions can be asked from the security perspective as well. But a few security-related specific questions that we have, that is somebody is running privileged containers or not. Because as we all know, that if the privileged container is compromised, then basically your host can compromise as well. And also what kind of containers are executing. We vet all the images that are being run through our ECR registry, but somebody is running some containers that we haven't vetted before, or we haven't scanned through our scanning system, and that could be compromised. So we tried few tools to solve these problems, right? We tried vendor-based solutions as well, and we tried open source solutions as well. And my background is in system security. In my PhD, I worked on a lot of system call monitoring and developing systems. So we were looking into a lot of tools to find out who can support our environment. And we decided to use Falco. Falco, as Kris mentioned a lot about that it's a container native runtime security. It is designed for the container, and it can provide all those things that we needed. And without going much into the detail, but definitely based on what Kris mentioned, that Falco has three main components, right? Rule and alerting engine that can tell you if something wrong is happening with your platform. Then agent that basically receives the system call and create metadata related to containers or events and basically give you a very clear picture of what is happening. And the kernel module or EBPF filter-based interception method that can actually capture those system calls. So this is what Falco provided, and Falco can give you alerts, right? If something bad is happening, it doesn't tell you what events, but it can tell you whether shell was opened or not, as Kris demoed. But we had few different requirements that we wanted to have, we were looking in a tool, basically. We wanted raw events. We didn't want to just get alerts. We wanted to get actual system calls. So the idea was that if we have actual system call, then we can build a lot of tooling around that, right? We can build machine learning AI-based systems sitting on top of the system call to give us a lot more attack detection capability rather than just a signature-based alerts that whether shell was spawned or file was accessed and so on. And we wanted to enrich those events, right? So Falco does a pretty good job in terms of collecting metadata related to event, but we wanted to have more events associated with our system call. For example, what kind of cluster it is running, whether it is running in ECS or EKS, what kind of VPC, which VPC it was running on, what load balancer it is accepting the request, and so on. So we wanted to have a lot more context around those events. We also wanted to have an easy to update rule process, right? For example, what happens that Falco rules sit on each machine, right? Each instances. So if you want to update those rules, either you have to use Ansible scripts to update those rules at runtime, which if it goes wrong, it can crash your cluster or VM, or you have to rotate virtual machines every time with the golden image with the new rule set in order for you to have new rules. So we didn't want to have that kind of setup. And we wanted to have a centralized alerting engine, right? Falco has a rule engine, but we didn't want to use that rule engine. We wanted to have a one rule engine across all services. So single rule engine that can support guard duty, AWS config, Falco, inspector, all those services. So these were the requirements that we were looking for in a tool. Apart from these sort of hard requirements, we had few soft requirements. We didn't want to manage our own cluster to support all those features that we wanted or extra features that we wanted, right? Otherwise, we had to manage or patch those VMs and we have to worry about our own cluster. We wanted to be very cost effective. We didn't want to boot big infrastructure to blow up the cost. We didn't want to look into scalability issues, right? We didn't want to go into auto-scaling group setup and so on, right? So, and last but not least, we wanted to have a very easy way to look into alerts, to respond to alerts. And before going into the hard requirements that like raw events and all those things, let's look into soft requirements a little more. And in order to realize these soft requirements, we decided to use serverless-based technology. We are in AWS, so we started using Lambda functions very heavily. And serverless function came out in last 2-3 years ago, where if you look into the offering, in the beginning, cloud providers were offering infrastructure as a service model, right? Where they were managing hardware and hypervisor, and customers were managing virtual machine, operating system, and application. That model got changed a little bit in the world of platform as a service, where cloud providers started managing VM as well, and then containers and applications were the responsibilities of customers. And this model got pushed to an extreme in the world of function as a service, right? Where cloud providers started managing hardware, hypervisor, virtual machine, operating system, and even the runtime, right? And the customers or tenants were just tasked with coming up with their own code. So if you want to run Python-based serverless function or Java-based serverless function, you don't have to worry about setting up JVM or Python environment. You just bring your own code, tell the cloud provider the entry point of your function, and cloud provider will start invoking it. And we decided to use serverless-based technology for our even to realize our hard requirements. And benefits of serverless directly translate to our soft requirements. That with the serverless, you don't have to manage any servers, right? Everything is managed by cloud provider. Continuous scaling, again, you don't have to worry about. Amazon, Google will worry about scaling those functions. So if you, in a peak time, if you want to run thousands of functions concurrently, cloud provider will run thousands of functions concurrently for you. Fine-grained metering, right? You only pay when the functions are invoked. So if in a off-peak time, if the functions are not getting invoked, you won't pay even a dime. And when the functions are invoked, that's when you have to pay. And faster time to market, right? Because we are bringing our own code, we don't have to worry about the setup and infrastructure related issues. So it's very easy to get yourself up and running. So there are many ways you can run serverless functions, and there are different models of running it. One is the default, a very common model where the way you run serverless function is called event-driven serverless function. So idea is that these Lambda functions or serverless functions will subscribe to some resources and then wait for events to get triggered. And as soon as events are triggered, they get context for those events. And with the context, they also get necessary information to process those events. So for example, Lambda functions can subscribe to S3 bucket and wait for put objects to happen. As soon as objects are inserted into the S3 bucket, the SNS event will be generated and Lambda function will be invoked. And Lambda function will get the context, the actual information about the object that is being uploaded. And Lambda function can process that object, do whatever it is supposed to do, and then it can go back to sleep. There are many other, so we are using event-driven model a lot in our extensions that we build for Falco. There are many other ways you can invoke serverless functions. And so we are using serverless function a lot. Our transcoding pipeline is written in serverless, and we use a lot of serverless function in the security team as well. And we actually came up with the 6 design pattern, and we wrote a research paper last year in the conference called Hot Cloud. And if you guys want to read about it, check it out. So let's look into what are the security components that we build for Falco. So there are 3 main components. One, we call it Falco on host, basically the way Falco runs, but we did change a little bit around it, about it. Then we developed a system called Driftwood, which is an analytic system that basically consumes the data generated by Falco and process it. And then we developed an alerting engine called Bobby. These logos looks very crappy because I had to change it because of copyright issues last minute. Because we were using some other ones internally, and I was told that I cannot use it in the talk. So let's look into Falco on host architecture. So this is the glorified version of what Kris showed you. So again, this is a single EC2 instance. And we are running a bunch of containers. All containers are generating system calls. And all system calls, normally system calls is the way for you to interrupt from user mode to kernel mode. So that's why system call goes to the kernel, and kernel module is actually intercepting all those system calls. And as soon as it is collecting the system call, it is pushing back through the ring buffer to the Falco agent. And Falco agent's job is to get these system calls, get metadata associated with those system calls for the system call, what container it is coming from, what's the image name, and so on. And also, it reads a rule file. And I'll tell you what the rule file does. But in a simplified way, this rule file tells Falco what system calls to collect and what to drop. And based on that, Falco decided, okay, this system call needs to be collected. Then basically it writes into var logs falco.json file. And as soon as file is written, each of these instances run CloudWatch agent, whose job is to read this file and push the data to AWS CloudWatch logs. Now, this is the setup even if you use Falco in a default way as well. You can have a EBPF instead of kernel module, but you will have a Falco rule file, you have a Falco agent. The way we are, in this design, the design that we are using, we are different in only few ways. First of all, our rule file does not contain any alerts. If you use Falco in a vanilla mode, this rule file contains all the alerts that Kris showed you, whether somebody is creating a shell within the container or some or /bin directory is being written. Those kind of alerts normally are in the rule file. But our rule file does not contain any of those alerts. Our rule file just contains few instructions for Falco on what system calls it should collect, what system call it should not. And we also have some filters to avoid to reduce the volume of data that is coming from Falco. And then we are using CloudWatch and to read the data and push it to CloudWatch logs. So what the rules, what those system calls are. So we wanted to know process. We wanted to capture process creation, file operations, and network connections. So we are monitoring execv for process creation, file open system call, and network connection connect system calls. We are monitoring eight or 10 more system calls, like a rename at, open at, unlink at, those kind of things that can tell you if somebody is doing some kind of anomalous operations. But again, rule file just contains what system calls to collect. So now we have Falco started generating the data. Data is coming in a very high volume. I will show you some numbers. So next step is Driftwood comes into the picture. Now, Driftwood's job is to collect the data that is being generated by Falco, enrich the data further, because that was one of our requirements to have more context associated with the data, and then visualize it, create plots, graph, and charts, sort of. So this is how Driftwood's pipeline looks like. Again, it's entirely serverless-based pipeline. So the goal was to create a generalized system that we can just not only use with Falco, but with other services as well. So Driftwood cluster is our analytic or threat intelligence cluster for all the data sets that we have. So even ELB log, VPC flow log, guard duty log, all kinds of log goes through our Driftwood cluster, and Falco log is one of the inputs. And we have a multi-account strategy. We have multiple AWS accounts. So you can see that on the left side, we have different accounts running different CloudWatch, because each of those accounts can run some VM and containers, and they all will be pushing the data through this Driftwood pipeline. So now CloudWatch is basically storing Falco data, WAF, web application firewall data. There are more data sources. And all these accounts will start sending data to the firehose. That's a AWS message bus. And when data goes through the firehose stores the data into the S3 bucket. And this S3 bucket has an event-driven Lambda associated with it. As you can see that S3 is generating SNS events, and this event-driven Lambda, we call it enricher Lambda, is getting invoked every time the log is written. When the log is written, AWS Lambda takes it, enriches it. I'll show you what kind of enrichment that we do. And then it stores in the Elasticsearch. And a copy of enriched data is also stored inside another S3 bucket for alerting purposes. And this enrichment that you'll see is customized for each type of data source. So for example, for WAF data might goes through different enrichment process compared to Falco data. And based on the data type at runtime, we can decide which processors to use to enrich the data. So some of the enrichment that we do, first of all, IP to geo mapping, right? We get a IP data, but we associate geolocations with that. Then IP to resource data. For each IP that we are getting, we can associate that whether this IP belongs to S3 or not, or whether it means this traffic is going through S3, or this traffic is going through NAT, or this traffic is going to load balancers. So that kind of enrichment that we do as well. And then instance to cluster type, that whether this instance belongs to ECS cluster or EKS cluster, or it's part of the transcoding pipeline, or it's in the web API pipeline. So, and we also attach VPC ID and all those things with the data set. So that basically realizes, so Driftwood basically fulfills our requirement of raw data and the enrichment data. So some numbers, right? So in a peak day, we process close to 240 million raw events that goes through our pipeline. These are just raw system calls, right, that we are collecting every day. On a given weekend, on Saturday or Sunday, it comes down to 76 million or 75 million, right? It's like a 10 million events per hour. The deviation and standard deviation and is almost same. So it's not that we see 100 million events per hour in a day. It's very consistent. But yeah, but we are processing 250 million, close to 250 million events every day. That is flowing through Driftwood and getting stored in the Elasticsearch and in the S3 bucket. So this is how a single record looks like. So if you have an open system call, right, that Kris showed you, this is all we are collecting for that single open. We are collecting which instance is coming from, its private IP, instance type, container name, container image, repository, VPC flow ID, subnet ID, and what file was opened, what process opened it, what was the parent process, and all those things. So as you can see that it's quite a bit of information, and their PIDs as well. Awesome. So now we have data that is being generated by Falco, and now Driftwood has processed that data, stored into the Elasticsearch because we use Elasticsearch as our SIEM, and also now data is also got stored into an S3 bucket. The next step is how we can use the data that we collected and that processed by Driftwood for actually alerting purposes, so we can get some security or we can get some visibility if something bad is happening. And for that, we developed, and again, a serverless-based alerting engine for the cloud. Idea is that Bobby is a centralized alerting engine that we use for all the services. And again, this is we developed in-house. It can take multiple input sources, so guard duty, AWS config, inspector, Falco, WAF, all these are sending their alerts through Bobby. And the name Bobby that we came up is like a UK police is called Bobby, and my developer was from UK. So he used that name. And it has a multiple output channels as well. So it can send alert at various places like a Slack, Ops Genie, Elasticsearch, PagerDuty. So it has all those integrations as well. And it can allow very easy whitelisting and throttling features as well, so that if the alerts are keep coming, you can whitelist them if you know it's a benign alert. And you can, if alerts are coming with let's say you are running 100 VMs and all of them saw the same event and all of them send the alert at the same time, you can use throttling feature to tell them, hold it back for you. So this is Bobby architecture. So again, it's using a lot of serverless event-driven Lambda functions. But now recall that we stored the Falco data in S3 bucket, the enriched data, right? So that S3 is pointing to that S3 bucket. Now this S3 bucket, as soon as data is stored, it again sends the event-driven Lambda SNS function and invoke the rule engine Lambda. And this rule engine Lambda's job is to take the data that is sent by Driftwood and read the rule engine file, our alert file that we have a centralized file in the database where, not centralized alerting database, where we can have all those rules crafted. The rules are very similar to what rules you see in the Falco file, but then you can, it's like a command ran out of temp, or shell was created, crypto mining is happening, and so on, and all those alerts. And rule engine will get the data from Driftwood, get the rules, and applies that, and decides whether it needs to alert the security team or not. And what we have also in the DynamoDB, a set of whitelist that we have already developed over time. So it also checks with the whitelisting option, saying that whether this alert needs to be generated or not. If it says that no, it's not in the whitelist, it's a new alert, then it can send it to multiple output sources, so Slack, Opsgenie, and Elasticsearch, with a appropriate priority. So whether we have to wake somebody up in the night, then it's a P1, P2. Otherwise, you can look at it when you are in the office. And from Slack, when you get a message on Slack, you can actually take action on those alerts. So you can either whitelist or you can ignore those alerts. And when you press the whitelist, there's the API gateway path from the Slack. Webhook gets fired, and it goes through API gateway and invoked another Lambda. And that Lambda basically stores that whitelist into the DynamoDB, so that a rule engine can look into the DynamoDB whitelist, and when the same alert happens next time, it doesn't have to alert us. So this is how config file look like, right? So it's based on object path language. So let's say alert is called command run out of temp, right? If that is the alert, then we have some conditions that if the system calls needs to be exec VE, and which is like event type, and we need to know some execution path or something. And then the notify tells you what are the notification channels, like Opsgenie or Bobby alert channel on the Slack. And all those bottom fields are telling you that what are the different combinations of whitelisting we support for this alert. So this is how actual alerts seen on Slack by our security team. So since it's the P1, so command run out of temp, so maybe somebody is going to be waking up in the night. This account is production, instance name is given, the process is AWS logs, execution path, you can see where that was executed, and that's why alert got fired, because this Python program was executed inside the temp directory, which it was not supposed to happen. Given that it is doing AWS logs, so it is false positive. So, but then we have an option to whitelist this alert. And you can see the entire command that was executed in order to run this thing. Here we are not showing you the whitelisting option, because generally we don't want to have this culture of whitelisting P1s, right? We want to go and look into P1s. We want to make a complete post-mortem, why it is happening, who did what, and so that we have a better idea of, so that we don't have this kind of P1s, or either it needs to be downgraded to P4, or if it's P1, we should know this should not happen again. So let's look at different alerts. We have this alert called unexpected process spawn, right? And since unexpected could be anything, it could be noisy, that's why we have at P4. And it says that this Kubernetes VM was running awk program. So again, awk is not very security sensitive, but we have not seen awk before from this VM, and this is a development VM. So when we see alerts from the development VM, we basically go ahead and either whitelist or take some action so that we can learn from this behavior, and same behavior should not be alerted when it happens in the production. And here you can see the whitelisting options. And these are the 3 whitelisting options that we have. And these whitelisting option changes depending on whether it's a networking alert or file alert or process alert. Since this is a process alert, we allow you to, we have this thing that you can whitelist just by being process name. So based on, so it will be whitelisted using process and execution path. If not, then it will be by, if you do process and parent, then process, execution path, and parent field will be used to generate a MD5 hash. So the next time when the same alert comes, all those fields will be used to decide whether alert is in the whitelist or not. And you can also go with the parents process and command line that is very extreme, where you just want to match a very specific behavior. Otherwise, you want to get alerted on that attack or on that event. So that's how basically with the changes, the way Falco runs on the host, with the Driftwood and Brobby, we basically changed the way Falco works in our environment. We have some other use cases as well, other than alerting security and visibility. We use Falco a lot during debugging process. Because we are collecting raw system calls, so we can see what is happening just by, when something happens, we can go and look into our Elasticsearch logs to see who has run what command at what time. We mainly use a lot during our game days when we do red and blue team exercise. When somebody runs something and we look into the Slack channel Ops Genie, whether those alerts are coming or not. And again, since we can see the raw events, we will know what is happening. And again, during the chaos engineering as well, when we want to make sure that we want to know or get visibility on what is happening. That's pretty much what I had. Key takeaway.
Questions? Yes. Well, actually, I'm supposed to come to you, so I'll do this.
Sorry?
If we get a copy of the slides, I didn't see it in the sketch app.
Oh yeah, sure. Yep, I'll upload that. We were just editing till the last minute, so.
Any other questions? Yes, here.
How long did it take to go from downloading Falco to logging and the infrastructure you put together?
I'm going to read it back.
That's a good question.
How long did it take to go from?
So one developer, 3 months. Yeah. Yeah.
So for the cloud native events, for any events in the cloud, the time matters. How long does it take for event to be triggered to the Slack and the team to react?
Few seconds.
Few seconds.
Yes, it's pretty fast. Because we are doing in real time, as soon as events are, so only latency that we have is the actual latency within the AWS services. So from Falco, as soon as logs are returned, since the things are happening pretty fast, events, if systems is being used, then you can see files are getting filled very fast. They get pushed to the CloudWatch log to...
It's not fast, that's what I'm asking.
Right.
Because I know that CloudWatch logs is not fast. It's not not even close near real time, it's like a minute.
So,
It cannot be seconds, so that's why.
no, okay. So depending on the type of alert that you are talking about, right? Few alerts you can see few seconds, few alerts will take a little bit, maybe few more seconds or few seconds to minute between, right? Because depending on how much events are being generated at that time, right? So that's log. If you are at the edge of the log, yeah, you can see very fast. But if you otherwise, you'll say at least. But we never see anything goes beyond a minute.
How you did false positive? No offense, but Falco is like giving a lot of things. How you dealt with false positive?
Right. So false positive is a real problem, right? So depending on, I think that's when you need to have a good system where you can run the same system in development that we are running and same system we are running in production, right? Falco, false positives are, it's not a machine learning based system, so it's a signature based system. So it's your appetite on what you want to see. For example, our alert, unexpected process spawned. By nature, it's a false positive, right? Because awk is not an alert, right? But the same thing is that we wanted to see that. We wanted to get the visibility. That's why we have these alerts, but we have kept it at P4. So it means that we don't want to be waking up in the night just for some unexpected process response, because we have other rules, more targeted rules are in place that can tell us when something bad is happening. So it depends on what kind of rule. So rule crafting is very important in any security tools, right? That if you craft a very generalized rule saying that any write into user local bin should be notified, then you will find that most of the time, even AWS agents and all those benign programs, even during the yum update, you might find that a lot of operations are being performed in that directory, right? So it means that you have to craft a rule in a way that either sometime you're looking for very specific operations, or you develop your whitelist over time so that you know that, oh, I'm not gonna worry about if yum does that, I'm not gonna worry about if RPM does that, and that's when you can narrow down or you reduce your false positive. For example, even an unexpected process is spawned, we narrowed down to one alert in a day, because we trained our system so much during the development phase that every time something happens, we went in and we whitelisted, we went and we whitelisted. And that's when our system was completely stabilized.
Two questions. How far left can you push that whitelist? For example, can it live in the Falco rule file? Is that appropriate? Or?
So by design, it lives with the Falco agent.
Okay.
Yeah.
So a little bit of just looking to the future on how we're managing rules right now. So right now we're using Lua and YAML to encapsulate the rules. The next big push for the next 6 months in the Falco open source community is we're going to be pulling out a lot of the native rule parsing that actually looks for configuration on disk, and we're going to expose that via an API. So basically the pattern is going to be, as Falco starts, it's going to start with no configuration, and it's effectively just going to be a very empty loop doing virtually nothing. And then you'll be able to start sending rules to it dynamically using a client of your choice, and you'll be able to create rules that way. And of course, we're going to increase backwards compatibility by just having a simple lightweight CLI program that parses rules as they're written today, and then just sends that out to the client accordingly. So.
And then the second part was not knowing much about Falco. Is it also responsible for like managing actions to take on a certain thing? So for example, here's an alert, but I also killed the pod or container at the same time.
So this is a big design here. I'll get back on stage for this one because this is going to take me a second. This is a big design choice that we made on day one. So I'm going to draw a quick comparison to SE Linux, right? And we're going to use SE Linux to the kernel versus prevention to Kubernetes. And this is what I was talking about earlier where I talked about prevention. So by design, Falco is not in the business of preventing anything from happening, right? Like we don't want to confuse surveillance with access control. Those are two independent systems that need to work independent of each other that are both necessary to have a secure system. So the pattern that we see most folks doing is detecting some sort of anomalous behavior, understanding what happened, coming up with a plan of like understanding what the attack vector was, what they did and what they were after, and then either through an automated process or through a manual process, responding to that event and generating prevention policy moving forward. If you would like to use Falco to, say, for instance, kill a pod or draft some OPA policy or email someone or destroy a cluster or nuke a VM or whatever, you certainly could write a tool to do that. Most of the time what we're seeing is Falco goes directly into a stateful aggregate time series database, and then there's some sort of like response and detection on top of that. Yeah.
So to say that back to you, Falco's more about surveillance today, and then what you want to do with that is kind of up to you.
Correct. And so like, for instance, Sysdig, the company I work for, we have patterns that we suggest in some of our offerings that say like, here's how one could respond to these events. But the Falco open source project, we try to keep the scope as limited as possible. And it's basically a surveillance tool, right?
And you can achieve some of these automation by yourself. Let's say in our design, when you do on Slack, say whitelist or it's an attack, you can run a Lambda function which can go and kill the pod, or which can go and take some remediation action the way AWS config does that.
Right, and if you look there's a train behind me. If you look in the Falco repository, we have a tool called the Falco Sidekick, and we also have one called the Prometheus exporter. As soon as we had the client go for the gRPC endpoint in Falco, folks began contributing very lightweight small programs to do arbitrary tasks. The Prometheus exporter just basically relays the information to Prometheus. Falco Sidekick can connect up to about a dozen different well-known open source tools and take action from there. So if folks are interested in contributing or using the client, we would love to get you involved with the Falco community.
So like those two tools you spoke about, like just coded copy and plans to like open source it.
Yes, we are actively thinking about it.
So like when do you think?
So we have to go through the process. We will be talking with Kris as well, and we have to do internal deliberation on that as well. Yeah.
We want to try to get them to donate it to the Falco project, but that's like our own secret agenda here.
That would save a lot of cost for us.
Sorry?
That would save a lot of cost for us.
Yep.
Last one, two more. So you?
It looks like a lot of the pieces of your the infrastructure that delivers all this Falco stuff is very like serverless oriented. Are you doing anything to correlate what's going on with serverless with what's going on in your pods?
What do you mean?
Just whether or not you're instrumenting the serverless in a way that feeds into this stuff as well, or if you're just using serverless mostly as a glue component.
Right. So yeah. So right now, serverless is a glue component, right? That basically taking actions, right? But yeah, I mean, we can, and maybe that's the reason for us to get raw events is to be more creative, right? We can do a lot more things because we have raw events, right? So maybe we can correlate with the VPC flow log. We can correlate with the web logs, firewall logs to build a better correlation model, right? To be better, more holistic picture of what is happening in the cloud, right? We can stitch events. We haven't done that, but it's in our roadmap.
Stupid question maybe, but with these EBPF program stuff, can't you accidentally write a stupid Dutch program that has also a negative effect on the system, the same way a kernel module can?
So the question was, can you do anything with eBPF that could basically have the same effect as a kernel module? So eBPF is read-only, right? So we're not actually able to generate like new logic and implement new logic into the kernel. With eBPF, we're able to read virtually any piece of address space from the kernel, and then all the code does is just simply echo that up in a meaningful map to user land. Whereas with the kernel module, we could actually go in and we could change things in the kernel, or we can mutate memory, and there's a lot of things we could do that could potentially harm our system. So that's why eBPF really is getting the hype it is because it's fundamentally safe because it's read-only. Sure?
No, right now we are running in the kernel module mode. No, Sysdig so Falco comes with the kernel module and eBPF designs. So yeah, so we are using kernel module design.
Yeah, so one of the things that we're doing right now, so we're in Sandbox, like I mentioned, we're moving to incubation for Falco. As we move into incubation here over the next month or so, hopefully we'll get it, we're going to be moving the infrastructure that builds these kernel modules for different kernels and operating systems. There's many permutations there, as I'm sure you can imagine, and building those and storing them and hosting them publicly for folks to download. And there's actually a hook in the Falco code that when Falco starts, it'll check to see if the /dev device is mounted, and if it's not, it'll attempt to actually do a dynamic URL generation to try to pull it out of S3 and install it on the system using dynamic kernel module loading. Cool. Thank you so much.
Thank you.